This presentation introduces VRU-Accident, a vision language benchmark for video question answering and dense captioning for accident scene understanding. The study focuses on accident scene understanding involving vulnerable road users, such as pedestrians and cyclists. Before proceeding, please note that this presentation contains real-world accident videos, which may be disturbing to some viewers. Viewer discretion is advised. In the following sections, the key contributions, benchmark design, dataset composition, and evaluation results will be presented. Previous research has widely applied vision language models for autonomous vehicle decision-making, thanks to their strong visual understanding. However, no benchmark currently evaluates their performance on accidents involving vulnerable road users, which are far more unpredictable than vehicle-to-vehicle cases. Pedestrians may jaywalk or appear suddenly from occluded areas, making accident prediction highly challenging. This highlights the urgent need for a VRU-specific benchmark. To address this gap, we introduce VRU-Accident, a large-scale benchmark of 1,000 real accident videos. It includes both video question answering and dense captioning tasks to assess models' visual reasoning and narrative understanding. We also design a semi-automatic pipeline that generates semantically rich question-answer sets and evaluates 17 state-of-the-art models. This unified benchmark provides new insights into the limitations of current models and guides future research towards safer autonomous systems. Our VRU-Accident benchmark is built on real accident videos involving vulnerable road users and defines two evaluation tasks: visual question answering and dense captioning. The VQA task, spanning 6 categories from weather conditions to prevention measures, evaluates both visual understanding and higher-level reasoning, such as accident causes and preventive strategies. Dense captioning, producing detailed scene descriptions, examines whether models can capture accident dynamics and spatio-temporal interactions between vehicles and vulnerable road users. Here are the statistics of the VRU-Accident benchmark. First, for the dense captioning task, we curated 1,000 unique accident descriptions. These captions allow us to assess vision language models' abilities to generate event-specific accident narratives, ranging from capturing the spatio-temporal relationship between vehicles and vulnerable road users to describing the key causal factors of the accident. Second, for the VQA task, each category contains 4,000 candidate options and 1,000 ground truths, resulting in a total of 24,000 candidate options and 6,000 ground truths. There are several important characteristics of these VQA annotations. First, the dataset contains a large number of unique options and ground truths. For example, the accident prevention measure category includes over 2,000 unique candidate options and more than 200 ground truths. Similarly, the accident cause category contains more than 700 candidate options and over 100 ground truths. This richness enables us to assess the generalizability of vision language models, unlike standard classification tasks, which have only a small number of fixed classes. Second, the dataset covers a diverse vocabulary across all categories. This diversity allows us to measure a model's capability of contextual understanding beyond simple word matching. Third, the dataset maintains a balanced ground truth distribution. As shown in the figure, each answer option, A, B, C, and D, appears with nearly equal frequency. This mitigates potential bias toward any specific answer, ensuring that models cannot exploit imbalanced label distributions to gain artificial performance. Last, we focus on the semantic similarity between questions and answers. We measured the cosine similarity between the question and its ground truth answer, as well as between the question and each distractor. The results show that the similarity of wrong answers is often comparable to that of the ground truths. In some categories, such as road configuration, accident type, and accident cause, the similarity of distractors is even higher than the ground truth. This means that the wrong answers are semantically plausible, and models cannot simply rely on surface-level cues or word overlap. Instead, they must achieve high-level understanding of accident scenes in order to identify the correct answer. Together, these statistics highlight the benchmark's ability to rigorously test models in terms of both generalization and contextual reasoning. Experiment. Our experiments reveal that current vision language models perform very poorly on VRU-involved accident scenes. This highlights their fundamental limitations in capturing the complex dynamics required for safe autonomous vehicle decision-making. Conclusion. This work presented VRU-Accident, the first benchmark designed to evaluate vision language models in safety-critical scenarios with vulnerable road users. Our evaluations show that while models handle basic visual attributes reasonably well, they consistently fail on spatio-temporal understanding in accident scenes. These findings highlight that current models are not yet capable of accurately understanding VRU-involved accidents, limiting their applicability to autonomous driving. VRU-Accident thus provides a unified and challenging testbed to advance research in this direction. For more detailed results and analysis, please refer to our paper.